For this lesson, we'll be going over nodal analysis. Nodal analysis is a network analysis procedure that uses voltages as the unknown. This will also be referred to as node voltage method or node analysis. And nodal analysis uses the equations based on the concept of Kirchhoff's first voltage law or first law. Input current equals output current, and we'll go over that more later. Now, just be aware, in electrical engineering, node refers to any point on a circuit where two or more circuit elements meet. So be aware, if you have a right angle or anywhere that's not considered a node, you can't count that as a node. It must be where two or more circuit elements meet or two branches off. Nodal analysis has 4 simple steps. Those steps consist of determine the amount of nodes required. This includes the reference or ground node. You must establish a fixed current direction for each node, and pretty much you guess the current directions. Next, and this is where the hard part comes in, which we'll go over in the examples, you write out the Kirchhoff's current law equations for each node. So your inputs, input current must equal your output current. And this next part, the number of equations is equal to the number of nodes minus 1. So if you have 5 nodes, you're only going to need 4 equations. 3 nodes, 2 equations, and so on. And then you're going to compute the voltages for the equations using your calculator. And I'm going to show you using my Casio 115. Now, when performing nodal analysis, there are pitfalls that usually trip people up. For example, each node requires a minimum of 1 input and 1 output. When current flows into the node, it must be able to flow out of the node and vice versa. You couldn't have a node with all outputs or a node with all inputs. So be aware when you're guessing your current flow directions to be able to have at least 1 input, 1 output. Next, be careful of the current directions when writing out your equations, which we'll go over in the examples, because some people put node 1 minus node 2 when it's not considered the case based on the current direction. So be aware, and we'll go over that in detail in the example. Next, mind the polarities of your current sources or voltage sources when writing your equations. If your voltage source is flipped a different direction, it may actually be negative 24 volts versus 24 volts. So be aware, and that will trip you up and that will give you false answers on your calculator, even though it will give you answers. Also, and this is very important, be aware of your calculator limitations. Now I'm using the Casio 115. That particular one can handle up to 3 equation matrices or 3 equations at once. However, that's as far as it can go. It can't go more than 3 equations at a time. Also, it does not compute any complex values. So I can't do any polar equations in this one. So just be aware of your calculator limitations. And again, we're going to show you how to use a little bit of your calculator in the examples. Alright, for this example here, this is a very simple problem that could be solved with simple Ohm's Law. However, we're going to tackle this with nodal analysis just to get our feet wet and kind of get refamiliarized with nodal analysis. So step 1, find the nodes. Now remember, the nodes is where 2 or more circuit elements meet. So for this one, this would be considered a node because we have 2 or more circuit elements meet, excuse me. So I'll consider that N1. And then we have another one down here, which I'm going to refer to as our reference or ground. Reason being is this would be considered our ground, but it is still considered a node. So I just refer to as reference 0 or ground. Step 1, we found our nodes. We have 2 nodes. Establish the directions. This is where you guess. You don't have to get it correct every time, as long as you follow the rules. It must have a minimum of 1 output and 1 input. So I'm going to say current's flow in this direction, and that direction. Same thing with this node. I'm going to say it's going in that way and back down that way. Seems logical, right? And then when you write our KCL equations, so n minus 1, I found 2 nodes, so a node minus 1. So we only need to write 1 equation. Again, we could have solved this with Ohm's Law, but I just want to get our feet wet with how to do nodal analysis. So, now with writing our equations, your inputs must equal your outputs. There's no getting around that. That's the best way to describe it. So we're going to need one equation, which is N1. So we're going to say inputs equals our outputs, so we're going to need to find our input side. Since we have one arrow going in, we just need to determine that side first. So it's going to be 100 volts minus N1 over 5 ohms equals. Now if you look at that, we have 100 volts right here, so it would be no different than 100 volts being right there. Then minus N1 over 5 ohms. So think of V over R equals I. That's basically the current flowing through that guy right there. Okay? Now we do our outputs. We need to do this branch and this branch. Well, I'm going to go ahead and cheat real quick and say when you add these two up right here, it comes out to be 35 ohms. Pretty simple because when you add 15 to 20, 35. They're still in parallel with the 10 ohm resistor, but just to keep it simple on us, we're going to do node 1 minus 0. So it's going to be this node minus this node, which is 0 or ground, over 10 ohms. Because your voltage right there over your resistance. And it's going to be plus, same thing, we have an output, so it's going to be N1 minus 0, because on the other side of these resistors we still have our same node. This whole area right here is this one node. So minus 0 minus your ground over, and this is 35 ohms. So you see how I did that? This is the input equals your outputs. Current in equals current going out. So we're going to simplify this equation and see it makes it easier for us to manipulate it. So start with the input side. So it's 100 volts over 5 ohms minus N1 over 5 ohms equals N1 over 10 ohms minus 0 over 10 plus N1 over 35 ohms minus 0 over 35. Okay, I think we could simplify this down again. Tell you what, let me move it real quick. So for this one it's going to come out to be 20 minus N1 over 5 N1 over 10. Now I'm not going to bring these down because 0 over 10 obviously is 0, so there's no point in adding that in there. So in a sense these don't exist. They're 0. There's no point in adding and subtracting zeros. So it's plus N1 over 35 ohms. And I think we can move this N1 over to this side. So it's going to be 20 equals N1 over 10 plus N1 over 35 plus, because we added the N1 over 5 from this side and added it to this side. So it's N1 over 5. So now we have an equation here that has different denominators. So we need to go back to our basic algebra and figure out where our common denominator is. Well, looking at this, I would say our common denominator looks like 70. If I want to make this 70, it's going to be 7 N1 over 70 plus 2 N1 over 70 plus 14 N1 over 70. See how I did that? I multiplied 14 times 5 to give me 70, and then 14 times N1 to get 14 N1, 35 times 2 to give me 70, and then 2 times N1, and so on. Just our basic algebra, how we did it back in preschool. Alright, so this would be our equation right here. Now we could simplify this down even further. So, going a step further, 7 plus 2 plus 14 comes out to be 23 over 70. And I think I can move this up here to give us room. So it's going to be 20 equals 23 N1 over 70. Well, again, still doing basic algebra. 70 times 20 comes out to be 1,400 equals 23 N1. And then we need to divide it by both sides by 23. So divide by 23, divide by 20, excuse me, divide by 23. 1,400 divided by 23 gives us an answer of N1 equals 60.87 volts. So if you took a meter between node 1 and ground, it would give you a voltage reading of 60.87 volts. Let's do another example and see if we can follow all 4 steps and compute it in the calculator the way we usually do it. Alright, for this next example, this one's going to be a little bit more trickier and this one's going to be a little bit more time consuming. However, if you're able to do this one, you can just about do them all. So we're going to follow these steps and see if we can come up with a final answer. So we're going to find our nodes. Well, I have one right here. We'll call that node 1. I have a node right here. Node 2. And I have a node right here. So that's node 3. And of course, we have to identify our reference node or ground. So we'll call that 0. Alright, so right now I have a grand total of 4 nodes. Okay, now we need to establish current directions. So I'm going to assume current directions. So I'm going to say current's going this way, and then going out of the node, and then out of the node. So we have at least one input and at least one output. Same thing here, since current is flowing to the right of this 4 k ohm resistor, I'm going to say it's going to keep going that direction, and then it's going to go to ground and to our next node. And then same thing here, since current is flowing through this 1 k ohm resistor up and around, let's keep that same flow. Same thing with this 3 k ohm resistor. It's going to the right, so we'll continue going that direction. And then it's going to go out to ground. So that looks like proper current flow for this diagram. So we found our nodes, we established current directions. Now we need to write our KCL equations. And since we have 4 nodes, we only need 3 equations. And since this is the area that trips everyone up, I'll try to do my best to go very slowly and surely in this area. So we'll start with equation number 1. Equation 1. We're going to start with node 1 since it just makes plain sense. We'll start from right here. So we have 24 volts. So it's 24 volts minus node 1 over 5 kilo. And that's our only input, so that's going to have an equal sign. Again, remember, your inputs must equal your output. So there's our input. And again, mind the current direction. So I put my 24 volts first because it's flowing this direction. So 24 minus 1. And I'm going to do the same thing once I get over here. So let's do our outputs. So we have current flowing from N1 to N2. So it's node 1 minus node 2 over 4 kilo. And it's going to be plus. Same thing. Node 1 is flowing to node 3, so node 1 minus node 3 over, and that's a 1 k ohm resistor, so 1k. Okay, now let's see if we can simplify this a little bit. Equation 1, this is 24 over 5k minus node 1 over 5k. This is going to be tedious, but we'll get through it. Node 1 over 4k minus node 2 over 4k plus node 1 over 1k minus node 3 over 1 kilo. And all I did was just break these up so that way we have common numerators just for now. Okay. Now, what I'm going to do is I'm going to try to move over here, so I'm going to divide that right there. I'll move this equation over here, but what I'm going to do is I'm going to move this node 1 over 5k to this side of the equation. So it's going to look something like this. So it's going to be 4.8 times 10 to the negative 3. If you do 24 over 5k, that's what you get. I'm just saving you one step, that's all. This is going to be plus N1 over 5k. All I did was just take this guy and add it to this end. Alright, plus, hopefully I can fit on this, N1 over 4k. And then we'll say plus N1 over 1k minus node 2 over 4k minus node 3 over 1 kilo. All I did was I try to keep them in order so all the nodes are together. So node 1, node 1, node 1, then minus node 2, minus node 3. That's all I did. I just moved them around a little bit so it's easier to follow. Okay. Well, we have 3 nodes here, node 1, that have 3 different denominators. So we need to find a common denominator. Well, looking at this just by glancing at it, I can right off the bat say 20 will work. So let's make node 1 have a common denominator, and then we'll be able to finish up the math equation for that one. So it's 4.8 times 10 to the negative 3 equals, to make 20 kilo, we need to multiply this equation by 4. So it's 4 node 1, 20 kilo, plus, and we have a 4k down here, so we need to multiply this times 5 and 1 over 20 kilo, then plus, well, this one's pretty simple, so it's 20 and 1 over 20 kilo, and then minus node 2, 4k, minus node 3, 1k. So when you add all those together, it's going to give us an equation of, if my pen will write, 4.8 to the negative 3 equals, and 4 plus 5 is 9, plus 20 is 29, so 29 node 1 over 20k, minus node 2 over 4k, and then minus node 3 over 1k. So I'm going to write this up top, that way I can erase all this. Alright, so we finished node 1. Now let's go to node 2. We're going to do the same song, different verse. We're going to do equation number 2 and do the same thing. So current is flowing from node 1 to node 2, and this is the input. So on this side of the equal sign we have N1 minus N2. Look at the current flow, node 1 to node 2. So that's over 4k. That's going to be equal, because we have to do our outputs now, because it has 2 outputs instead of 2 inputs. So this one's pretty simple, so it's node 2 over 2k. And I could put minus 0 here, that's fine. So node 2 minus 0 over 2k, that's plus. Then we have node 2 minus node 3 over 3k. Alright, so we need to simplify this down. So what I'm going to do is node 1 over 4k. My k's look weird, don't they? Minus node 2 over 4k equals node 2 over 2k. I'm not going to write 0 over 2k. There's no point. We're going to save us a little time on that one. It's going to be 0. So node 2 over 3 kilo, and then minus node 3 over 3 kilo. Make sense? All I did was just break these up. That's all I did. The bottom equation does equal this top one. It's just broken up a little more. Alright, so we'll see if we can cut that through and finish up this equation, see if we can simplify it again. So what I'm going to do is I'm going to put 0 equals, and I'm going to move these guys to this side of the equation. So it's going to come out to be negative node 1 over 4k, and that's going to be plus node 2 over 4k plus node 2 over 2k. I'm just keep going with it. All I did was move these over and then keep writing these out. So node 2 over 3k minus node 3 over 3k. Alright, so let's move this so we can see what we're doing. Alright, now node 2 needs to have a common denominator, same as the last one. Well, looking at this, I can see you can make that a 12. Easy. So 0 equals negative node 1 over 4k plus, well, to make that a 12, we need to multiply this one times 3, so 3 node 2 over 12k plus, well, to make this a 12, I need to multiply it times 6, so 6 times n2, or node 2, gives you 12k, plus, multiply this one times 4, gives you 4 node 2, 12k, and then minus node 3 over 3k. Let's see if we can get a simplified answer out of this one. node 1 over 4k plus 3 plus 6 plus 4 gives us 13. So it's going to be 13 over 12k. And then that's node 2. And that's going to be minus node 3 of 3k. And that's our next final equation. So what I'm going to do is I'm going to move this up here so that way this one's easier to track. So as of now, I have two equations accounted for. Last one, node 3. So equation 3. I seem to run out of room really quickly. Alright, so this one we have two inputs and one output. So let's do our first input, which is node 1 minus node 3. And again, look at the current direction. It's coming from node 1 to node 3. So it's node 1 minus node 3 over 1 kilo. And this is going to be plus, we have another input. Current direction is going towards node 3, so it's node 2 minus node 3 over 3 kilo. This theory that trips people up, keep in mind these current directions. It's not going to be N3 minus N2, it's going to be node 2 minus node 3. Okay? Equal sign, because we have one output. Node 3 over 6 kilo. And again, I can put minus 1, so it's node 3 minus 0. But we're going to cancel that one out anyway. Alright, let's simplify this down. So we're going to have node 1 over 1 kilo minus node 3 over 1 kilo plus node 2 over 3 kilo minus node 3 over 3 kilo equals node 3 over 6 kilo. And I just disregarded because this would come out to be 0 over 6k, so I just pretty much decided not to write that. Again, save us time. So you see what we have here? So what I want to do is I want to move all these equations to the one side, or all these variables to the one side. So let me cut it off right here. So I'm going to say 0. I'm going to write a little bit smaller. It's going to be negative n1 over 1 kilo. All I did was move it over this side so it becomes a negative. Let's do n2 next, just because it makes it easy on me. Minus n2 over 3 kilo. Now it's going to be plus n3, or node 3, over 1k, because since it's a negative sign over here, we're going to move it over and it's going to become a positive. Then we have another negative, it's going to become a positive, so it's going to be another again, plus node 3 over 3k. My handwriting's getting worse. Plus, and this is our last one, node 3 over 6k. So node 3 over 6k. Same thing as last time. When you have a common denominator here, this one's easy. Make it a 6. Because we have a 6 here, and you can do the same with 3 and 1. So I'll just bring this node down right here. 1 kilo minus 3 kilo. Okay, makes it easier to see. Plus, I need to multiply this node right here times 6. So it's 6 node 3 over 6k. Plus, this one's going to be times 2. So 2 node 3 gives me 6k, and then plus, and that's not going to change, 6 kilo. All I did, same thing as last time. Since I needed to make this 6 kilo, I had to multiply the numerator times 6, and same thing with this one, times 2. So, last time, 0 equals negative node 1, 1k, minus node 2 over 3k, plus 6 plus 2 is 8, plus 1 is 9. 9 node 3 over 6 kilo. That is our final equation for our last node. So let's write this guy up here. So now that we have our equations right here, we should be able to put this in a matrix. So I'm going to try to make a somewhat decent looking matrix. So it's going to be 29 over 20 kilo, and then negative 1 over 4k, and then negative 1 over 1k, next row, negative 1 over 4k, and then 13 over 12k, minus 1 over 3k. Then we have 1, negative 1 over 1k, negative 1 over 3k, and then 9 over 6k. Okay. I know it looks sloppy. I'll see if I can clean that up a little bit when we do the calculator. But let's see, so it's 4.8 times 10 to the negative 3, 0, 0. So this is node 1, node 2, node 3. Now you can see the reason why I made node 1 go first, then node 2, node 3, because that's how it's going to look in the matrix or the equation function. So alright, so now we can plug and chug in our calculator. Now I'm not going to show you the matrix mode function. I did that in mesh analysis, so we're going to stick to the quick and easy way, which is equation mode. So hit mode, number 5 equation, and since this is a 3 variable matrix, it's going to be a 3 by 3, which is option 2. And now we're going to input our variables, which is 29 over 20k. I'll just write out the 20k. Then I have negative 1 over 4k. 4k. And see if I can go a little quicker if I can. It comes out to be 4.8, negative 3, and negative 1 over 4k. Takes a while putting all these in, but I ain't to worry. As long as we get the right answer, that's all that matters. And over 3k, and that's going to maintain a 0. So go back to the beginning. So it's going to be negative 1 over 1k. The real good thing about this calculator is if you ever mess up, it'll let you go back and fix it even after you hit the enter button. So if you did all this work and you find out you fat figured in one thing, it's very easy to fix. Okay, 0 again. So hit enter. Now we have final answers of node 1 equals 8.535 volts. Node 2, 3.99 volts. And node 3 is 6.577 volts. All right, those are our final answers. All right, now we got our final answer of node 1 equals 8.54 volts. Node 2 equals 3.99 volts. And then node 3 equals 6.58 volts. So this right here took us quite a bit of time to go through, and I wouldn't expect you to do this very quickly. However, if you're able to do this one, you could do just about any problem using nodal analysis.